Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture 59 of the course Theory of Computation. In the previous two lectures, we saw introduction to the space complexity. We saw what is space complexity. We saw the space complexity model. We saw the relationships between space complexity and the time-bound complexity classes. Right. Then in the previous lecture, we saw NL completeness. Right. And in this lecture, we are going to see an important theorem in space complexity, which is Savitch's theorem. Right. Savitch's theorem relates the space requirement of the non-deterministic space-bounded Turing machine and the deterministic space-bounded Turing machine. To be more precise, it states that if a language can be computed by a non-deterministic space-bounded Turing machine that uses Fn space or OFN space, the same language can be decided by a deterministic space-bounded Turing machine by Fn squared space. So, non-deterministic space-bounded Turing machine using Fn space can be the same computation can be done by a deterministic space-bounded Turing machine in Fn squared space, right? So basically, we can let go of the non-determinism if we just use up the square of the space, right? If we can, we can leave the non-determinism by just squaring the space usage, right? So it's a kind of a surprising result, especially when we look at it from the perspective of what we saw in time complexity. For instance, SAT was in non-deterministic linear time. So if you have a non-deterministic Turing machine that runs in linear time, you could decide, let's say, 3 SAT. If we had a similar result, right, n time Fn is contained in d time Fn squared, such a result does not exist. If it was there in time complexity, this would imply that SAT is decidable in order n squared time, which we know would be a huge thing, but that is not the case, right? In fact, we still don't know if there is any polynomial time algorithm for SAT, right? So that way this is surprising, and in fact there are a couple of other results also in space-bounded complexity classes. The results are very surprising, especially when we contrast with the similar results in time complexity or similar classes in time complexity. So this is one of such results, and as we will see, the proof is going to be extremely simple and straightforward, right? It builds on some of the things that we have already seen in the previous lectures. So we saw that to decide whether a space-bounded non-deterministic Turing machine accepts a certain input string, we just have to look at the configuration graph and see whether there is a path from the starting configuration to the accepting configuration. Of course, we need to assume that there is a unique accepting configuration, but we have already discussed how to get to that. This is a relatively easy thing to accomplish, right? So now the focus is going to be, so you have a language A, right? Suppose you have a language A, which is an arbitrary language in n space Fn, right? We will show that this A belongs to d space Fn squared, right? So suppose A is decided by a non-deterministic Turing machine called n, which decides it in OFN space, right? N decides A in OFN space, right? Now, in the previous lectures, we have seen that such a machine has such a machine has 2 power OFN configurations, and since it is better to be like specific than asymptotics, right? So instead of saying things like 2 power OFN, it is better to have a specific number at hand. So let us say that the constant hidden by this O is D, right? So let us say that there are 2 power D Fn configurations for the Turing machine n, right? So maybe I'll just highlight this. So the Turing machine n that decides A, the non-deterministic Turing machine n, it has 2 power D Fn configurations, right? So this is an upper bound, right? So we'll just choose D to be the appropriate constant so that this is satisfied, right? We know such a constant exists because of the calculations that we did in the previous lectures, right? We just didn't really like the exact constant will depend on the exact Turing machine that we are looking at. Now, for this Turing machine and amongst these configurations, there is an obvious graph, right? So each configuration will have some number of successor configurations, right? Because it's a non-deterministic Turing machine, right? So we will have some. If you remember, the picture was something like this. The C start may have some successor configurations, right? So and it could be like there could be multiple successor configurations because it's a non-deterministic Turing machine, right? So there could be various directions it goes, and we want to check whether there is a path from C start to C accept. Right, so we want to see whether there is some computation path that goes from, let's say, C start to C accept, right? If it is there, then the input string is accepted, right? So C start is also specific to the input string, right? For the Turing machine n on a certain input string, right? So the starting configuration will change based on the input string. In fact, this entire configuration graph is drawn for that particular input tape content, right? So now we have to decide this on this graph, right? So we have a traversal algorithms, all that, but right now the goal is to decide this in space bound OFN square, right? Where then in space bound OFN square. And the idea that we will use is very, very simple. So all we are saying is that if there is a path from, let's say, V1 to V2 that takes t steps, right? If there is a path from V1 to V2, let's say that takes t steps. So please focus on this part, right? If there is a path from V1 to V2 that takes at most t steps, right? Then there should be a center vertex, right? Or there could be more than one, but there should be one vertex such that V1 to W there is a path. So the one central vertex that I am calling it W, there should be a path from V1 to W of length at most t divided by 2, and there should be a path from W to V2 of length at most t divided by 2, right? So this is the basic idea, right? If there is a path from V1 to V2 of using at most t vertices, then there should be a vertex W such that there should be a path from V1 to W using at most t by 2 and W to V2 using at most t by 2. So maybe I'll just do one thing. I'll just put this thing in a box. So right, so this is right. So this is the main idea here. So now we want to check whether there is a path from C start to C accept. So let us first explain a generic thing. So we accept if we just check whether T1 equal to T2, sorry, V1 equal to V2, sorry, this is an error. We accept if V1 equal to V2 or if there is an edge from V1 to V2, right? Basically that is the only way that we could have a path of length at most 1, right? Otherwise, if T is not 1, so there has to be such a vertex W that we just explained, right? So what is the W? We don't know that W. So because we don't know, we just try out all possible such W's, right? We just go through the list of vertices one by one and see whether for any W, is it the case that there is a path from V1 to W of length at most t by 2 and W to V2 of length at most t by 2? And if both of them accept, then we accept, right? So once again, the algorithm is the following. If t equal to 1, we accept with the simple conditions. If t is not 1, we check whether there is a path from V1 to W of length at most t by 2 and W to V2 of at most length at most t by 2 and accept if we both accept. And this W, we don't know which W it is, so we just try out all possible W's. And if any w this works out, that's fine. We have a path from v1 to v2 of length at most t, right? So now this is the algorithm. Now we'll have to just what should be v1, what should be v2, what should be t. We have to just say the space usage is at most d fn squared, right? These are the two things that we have to show, right? So v1 is c start, v2 is c accept, and t, we set t to be the total number of vertices, right? Because this is a graph and it has 2 power d fn vertices, right? That's by assumption. We said that it has 2 power d fn vertices. So if there is a path from c star to c accept, there has to be a path of at most 2 power d fn vertices, because that is the total number of vertices. If there is a path without reusing any vertex, right? So the maximum, like if you have a graph with 10 vertices or 100 vertices, the farthest apart 2 vertices can be of length 100, right? You can have a path from A to B of length 100, but not more than 100, because the total number of vertices itself is 100. So we just need to check whether there is a path from C star to C accept that uses at most 2 power d fn vertices, right? So now let's see the space usage, right? So initially we have v1 equal to c start, v2 equal to c accept, and t equal to 2 power d fn. Sorry. Maybe I should also mention initial call has C start and v2 equal to c accept, right? And then what we do is we use recursion, right? So what happens is we use recursion in this, right? So because this is what is happening here. The same algorithm, the same function calls itself. So it is kind of like a recursion. So if initially the parameter was t, I'm referring to this parameter, the inside calls, it makes 2 calls of where the parameter is t by 2, right? So initially we have 1 call with t and then 2 calls of t by 2, and then each one of them makes 2 further calls of t by 4, and each one of them makes further calls of t by 8, and so on. So we need to look at the total space usage. So let's see what is space usage, right? So here in this case we have to store v1, v2, and then a counter for w, right? And then we also need to store t, right? But then the thing is that when we make these recursive calls, at some point we will get the answer back, and then we have to continue the computation. So when you have multiple nested recursive calls, we have to keep remembering all the data that was relevant of all the recursive calls that we have made in memory, right? So if we are let's say the third deep or the third nested recursive call, we should remember where we were in the first time, the second time, and so on, right? So for each recursive call we need to keep this memory, right? So it's not just having to remember v1, v2, w, etc., v1, v2, w, t, etc. We actually need to remember v1, v2, w, t for all the nested recursive calls, right? So in fact I think I need to mention w also, right? So maybe w also. I think I'll just edit it, right? And I'll say right. So now let's see how much we need to remember. So we need to remember v1, v2, t, and w at each recursive call. And let's see how. So v1, v2, and w are vertices. We know there are 2 power dfn vertices. So the label associated with each vertex has dfn bits or dfn space is required. So log of that many bits, that much space is required, right? So there are 2 per dfn vertices. So if there are, let's say, 64 vertices, then, or 63 vertices, we need 6 bits to remember which, or we need a 6-bit label to separately name each vertex, right? Similarly, there are there are 2 power dfn vertices, so we need dfn bits to separately name each vertex. So each one of v1, v2, w require dfn bits, right? And t, we have also said that t is 2 power dfn. So even to keep track of t, we need dfn bits. So all of this requires dfn bits. So that is the space required at each recursive call. So dfn times 4 of these, so it is 4 times dfn, right? And how? And then the thing is, I mentioned that we have to make this, we have to keep this thing in mind or in memory whenever we make a recursive call. So the next question is, how deep is this recursive tree? How deep is this recursion tree, right? So t will become t by 2, t by 4 and so on. But how many levels can it go? So we know that the base case is when t equal to 1. So how many levels does it require for it to reach 1? So every time it halves, so we need log t levels for it to reach 1. So this tree has log t levels. So the number of levels is dfn, which is just log t, right? So the space usage is, now the space usage is 4 times dfn per recursive call, and the number of calls is going to be at most dfn because that is the number of levels. So the total space usage is, okay, so we replace 3 by 4 by 3 by 4, so maybe I'll make it 4 here, but that wouldn't really make a difference. So total space is 4 times dfn squared, right? And which is again, like 4 and d are a constant, right? So d is some constant based on the configuration tree, right, which is based on the non-deterministic Turing machine, and 4 is of course a constant. So it is OFN squared, and that's it. So just by a simple algorithm, we have shown that a non-deterministic Turing machine that uses Fn space can be simulated by a deterministic Turing machine that uses OFN squared space, right? And the algorithm is very simple. We want to check whether there is a path from starting configuration to the accepting configuration in a graph with t vertices, where t is 2 power dfn, right? So in other words, if there is a graph with 2 power dfn vertices, we want to check whether there is a path from one vertex to another vertex. So we just check whether that uses at most t vertices, the path that uses at most t vertices. So this is a recursive algorithm. If t equal to 1, it is straightforward. Otherwise, we just make recursive calls by trying out all possible intermediate vertices. Notice that here it is not a non-deterministic guessing. It is just that we are going to try out each possible w. This is okay, right? It's okay to just spend time on this because we are not paying by time. We are just paying by space, right? So, and the space usage is that each level we need to store v1, v2, wt. So that requires dfn space for each of these. So it's ODFN. And number of levels is the height of this tree. That's also dfn, like log t. So it's dfn multiplied by dfn multiplied by some constant. So it's order dfn whole squared, which is like d is a constant. So it's ODFN squared. Sorry, OFN squared. So that is a total space requirement. So this shows that how you can simulate a non-deterministic space-bounded Turing machine using a deterministic space-bounded Turing machine just by squaring the space usage, right? So this is a very surprising result. And one more point is that we don't. So here we we are actually using, we need to know what is the space usage of n, right? What is the space usage of the Turing machine that decides A, right? That is one thing that we are using here. We are using what is the space usage of n, because 2dfn and 2 power dfn is being used in the initial call of path, right? So we don't even need to do that. We can, if we don't know fn, right, we could just try out fn equal to 1, 2, 3 and so on till we get some fn for which we know we get an answer. Either we get that it is reachable, like the accept configuration is reachable from the starting configuration, or at some point we'll get that nothing more is reachable. At some point, trying out fn equal to 1 and fn equal to some value and the next value, it is not going to improve things. So when that happens, we know it is not reachable. So we can just try out one by one. And that will also, even if we don't know fn, right? So that is another small point. Even if we don't know fn, we can just try out fn one by one till we hit an fn where we get to know for sure. So that is Savitch's theorem. As I said, it's an extremely simple theorem, simple proof, and the result is very powerful, right? N space fn is contained in d space fn squared, and it is surprising. Let me just summarize by stating some consequences of it. So we saw NL, which is non-deterministic logarithmic space. So it is n space of log n. This is contained in d space of log square n, right? So log n becomes log square n. N space of n is contained in d space of n squared, right? So SAT is in n space of n and it is in d space of n squared, right? So this is very surprising. If we had an analogous thing for like this in time complexity, we would have shown that SAT is in d time n squared. And the third point is very interesting. So if you recall, when I defined when I introduced some basic space complexity classes, I just defined three: L, which is log space; NL, which is non-deterministic log space; and P space, which is polynomial space, right? So P space was defined to be union of all, so in fact this was P space, right? Union k equal to 1 to infinity d space of n power k, right? So I just defined three names: NL, L and P space. So some of you may have wondered why I did not define the non-deterministic equivalent of P space, right? Because in time complexity we defined polynomial time P and immediately we defined non-deterministic polynomial time NP. So similarly, shouldn't there have been, like when I defined polynomial space P space, shouldn't there have been a non-deterministic analog like NP space, right? So there is a reason why I didn't define it at that point. The reason is that due to Savitch's theorem, the non-deterministic analog of P space is the same as P space. Why? Because, so suppose, let's say, just for the sake of understanding, let us assume that there is such a space, NP space, which is a union of all n space n power k, right? All polynomials space bounded languages of n power k ranging from k equal to 1 to infinity. But then by Savitch's theorem, right? By Savitch's theorem, n space n power k is contained in d space n power 2k, right? So each polynomial, so whatever was contained in n space n is contained in d space n squared. Whatever was contained in n space n squared is contained in d space n power 4. N space n cubed is contained in d space n power 6 and so on. But then once we have this, all of this is contained in d space n power k from when k ranges from 1 to infinity, right? So basically what this is saying is that non-deterministic polynomial space is contained in deterministic polynomial space, right? And obviously the other direction inclusion is trivial, right? Anything that is deterministic is obviously contained in non-deterministic. So this shows that non-deterministic polynomial space and deterministic polynomial space are one and the same, right? So this is the reason why I did not define it then. So because nobody studies NP space, because it's the same as P space. So this is yet another contrast as a consequence of Savitch's theorem, right? Like while P versus NP, polynomial time versus non-deterministic polynomial time, or deterministic polynomial time versus non-deterministic polynomial time, is probably the biggest open problem in theoretical computer science, perhaps all of computer science. But when we move to space complexity, deterministic polynomial space is the same as non-deterministic polynomial space. There is no open question, and the proof is just what we just saw. It's extremely simple, right? So these are some of the consequences. So these are some of the consequences of Savitch's theorem, right? Right. So Savitch's theorem states that non-determinism can be traded off by squaring the space, right? And the proof is extremely simple by using a algorithm that decides whether there is a path from one point to another point, one vertex to another vertex, using at most this many intermediate vertices. And the idea is just recursion, right? And that completes this lecture, lecture number 59. That completes this lecture. So see you in next lecture, lecture number 60. Thank you.